Hi students, Professor Gray here. Today we need to talk about Kw. So in the last lecture, we talked about the acid ionization constant Ka and the acid ionization constant expression, which we write like that. So the expression is the whole thing and the constant is Ka, or the number value that goes along with Ka that's written in this column right here. Okay, so just a tiny bit of difference between the constant and the constant expression. And then we did the constant expression for base. So the base ionization constant is Kb, and the base ionization constant expression is this whole big thing right here. And again, the numerical values for Kb are on the chart, and they were towards the right-hand side of the chart. And today we have to talk about another kind of K, Kw. So looking at this slide right here, it's talking about the autoionization of water. And auto means that it's going to do it spontaneously all by itself. So what we have is we have this equation down here, and it's showing us that a water, which looks like this, is going to split up into H plus and OH minus. And by this point, we know that H plus doesn't exist in solution on its own. We know that it hops on water. So a better way to think about this is that we have a couple of waters that get together, and one of them gives its hydrogen to another water. So you can see over here that this hydrogen right here is gonna hop onto that oxygen right there. And we see that we create a hydronium, which is H3O plus, and a hydroxide right here, which is OH minus. So if we were to write out the balanced equation, it would look like this. Now, if you guys go on to organic chemistry, what you'll notice is the arrow that I drew right here for the hydrogen hopping onto the water will make your instructor cringe, because the arrow should actually go the other way, because we always have the electron pairs, the lone pairs, reaching out to grab the H plus like that. So just in case, there you go. All right, so autoionization, also called self-ionization. So we're taking a couple of waters and we're changing them into ions. So you can see that we've got a +1 charge here, and we've got a -1 charge there. So we've got ions. And this doesn't happen very often. It happens approximately 1 out of every 10 million water molecules will do this. So we don't have a whole lot of hydronium and hydroxide sitting around in regular water compared to the numbers of regular water molecules that we have. But it does happen spontaneously. And just in case you like the ball and stick model, here it is down here. Okay, so regular old aqueous solutions, or beakers full of water, are going to contain a few hydroxides and a few hydroniums, just because you have the autoionization of water. And they'll be in equal concentrations if we just have a neutral circumstance, meaning we don't have acid or base going on, okay? So the ion product constant for water is called Kw. And how do I get the expression for Kw? Well, if I write out my balanced equation, we had 2 waters, and those turned into a hydronium and a hydroxide. Oops, I don't want to put the parenthesis right there. I want to put the parenthesis right there. Okay, so that would give us K is equal to, and remember we have the concentration of the products on the top, And we have the concentration of the reactants on the bottom. So we can do a couple of waters like that, or we can realize that we're multiplying them together, and we can go ahead and put a 2 up there. Now again, the change in concentration of your hydronium and hydroxide, when you add a couple more or you take a couple away, it's going to be really meaningful because you don't have a lot in the first place. But if you change the concentration of your water by 2 or 4 molecules of water, it's not going to really change it a whole lot because there's so many of them. So we can do what we did for Ka and Kb, where we just go ahead and say, okay, the change in the concentration of the water isn't meaningful, so we're going to ignore it. Or if you really don't like to do that approximation, you can say, okay, well then I'm going to multiply both sides by the concentration of water squared, and that cancels out on this side, and then we will just call this guy right here Kw. So what that means is that Kw is now equal to the concentration of hydronium times the concentration of hydroxide. Now, this number is a constant, and it's always going to be 1.00 times 10 to the negative 14th, okay? So in pure water, what that means is that the concentration of hydroxide is going to be 1 times 10 to the negative 7, and also the concentration of hydronium is going to be 1 times 10 to the negative 7, because when you multiply those two things together, 1.00 times 1.00 is 1.00, and when you have a negative 7 as an exponent and a negative 7 as an exponent, when we're multiplying, we add those, which is a really strange thing that happens in math, but that's what happens. And negative 7 and negative 7 become negative 14. So again, pure water, we're going to have equal concentrations of hydronium and hydroxide, because you have to have this reaction happening here, and if you get one hydronium, you got to get a hydroxide, so they have equal concentration. Now, if we change the concentration of one of them, so say we increase the concentration of hydronium, then we're going to have to decrease the concentration of hydroxide. And if we decrease the concentration of hydronium, we're going to have to increase the concentration of hydroxide, because Kw is going to always want to be at 1.0 times 10 to the negative 14, so it will adjust. So these things are inversely proportional. If one goes up, the other goes down, and vice versa. Now, what does that look like in picture form? Because you might be at the point where you're like, what on earth are you talking about, Professor Gray? Well, here we go. This might be a little bit easier if we put it in picture form. So if we have pure water, what we're going to have is a concentration of hydronium, H3O plus, right here. That is 1.0 times 10 to the negative 7. Okay, so 10 to the negative 7 is same as 1.0 times 10 to the negative 7. And also you'll notice that the concentration of hydroxide is 1.0 times 10 to the negative 7. So that's right there where we are neutral. So right here where we have the same concentration of hydronium and hydroxide, we are neutral right there. Now notice as you get more basic, so you're increasing the concentration of hydroxides, you'll see that the picture of the OH gets larger, which makes that obvious that the concentration of hydroxides are increasing. And the picture also shows you that the concentration of hydroniums, or H pluses, are decreasing. So large hydroxide, small hydronium. And remember, we use H plus and H3O plus, which is hydronium, interchangeably in chemistry. And also notice that if you have a concentration of hydroxide that is 1.0 times 10 to the negative 1, what you'll have is the concentration of hydronium. That is 1.0 times 10 to the negative 13. Now, if you add up negative 1 and negative 13, what do you get? You get negative 14. So that should make sense to you guys. So going from negative 7 to negative 1, that's actually an increase because negative 1 is less negative than negative 7. So we're increasing the concentration of hydroxide, and what we're doing also, if we go this way, is we're decreasing the concentration of hydronium, okay? We're going from negative 7 to negative 13, and negative 13 is a lot more negative than negative 7. Okay, so what happens when we increase the concentration of hydroxide even more? We have 1.0 times 10 to the 0 power. Now, anything to the 0 power is what? Is 1, okay? So 10 to the 0 power is 1. So that's saying 1 times 1. So this is equal to 1 here. And then we've decreased the concentration of hydronium to 1.0 times 10 to the negative 14. And 1.0 times 10 to the negative 14 times 1 is what? It's 1.0 times 10 to the negative 14. So this should be sounding familiar to you guys. So whatever the concentration of the acid is, when we multiply the concentration of the base by that, we're going to get a 1.0 times 10 to the negative 14. And look this direction. So if we're increasing the concentration of our hydronium, so we're increasing our H+, so we're getting more acidic. We would be decreasing the concentration of hydroxide. And if we go from negative 7 to negative 3, that's actually an increase. So we've got 1.0 times 10 to the negative 3 here. And down here, we've got 1.0 times 10 to the negative 11. And this is all in molarity, so it's moles per liter. So you've got the M there. What we find is that you've got negative 3 and you've got negative 11. And those things, when you multiply 1.0 times 10 to the negative 3 times 1.0 times 10 to the negative 11, you get 1.0 times 10 to the what? Negative 14. Okay, so 14s and 7s and 0s, those numbers should start sounding familiar, especially 7 and 14. Okay, and then at the bottom it says, even though it may look like it, neither hydronium nor hydroxide will ever be a concentration of 0. So there's always going to be some H3O plus around, and there's always going to be some OH minus around. Even if you have a super duper acidic solution, so there's tons of H3O plus, you'll still have a random hydroxide OH minus in there somewhere. Not a whole lot of them, but there will be one or two. Alrighty, moving on to the next slide. So what does that picture look like if we write it out? Well, neutral solutions are going to have equal concentrations, and remember the brackets mean concentrations of hydronium and hydroxide. So the concentration of hydronium is equal to the concentration of hydroxide, and they're both going to be 1.0 times 10 to the negative 7. And that's going to be molarity, so moles per liter. So if we have the concentration of our hydronium times the concentration of our hydroxide, we would have 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7, and that's going to give us 1.0 times 10 to the what? Negative 14. Ding, 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 ding. Okay. Now, if you have an acidic solution, you're going to have more hydronium than you have hydroxide, because that's been the definition of an acid so far in this class, is that it's something that's going to be able to give away an H plus, and remember the H plus hops on the water, and that's the form that it stays in. So acidic solutions, yeah, they're going to have a lot of hydronium around and not very much OH minus, because hydroxide is a base, okay? So the concentration of hydronium is greater than the concentration of hydroxide in an acidic solution. So the concentration of hydronium will be greater than 1.0 times 10 to the negative 7, and the concentration of hydronium will be less than 1.0 times 10 to the negative 7. And when you multiply them both by each other, you're going to get 1.0 times 10 to the what? Negative 14. And again, this will be molarity and this will be molarity too, okay? Or we say molar, it's moles per liter. Now in basic solutions, also called alkaline solutions or alkali solutions, you're going to have more hydroxide around than you're going to have hydronium, okay? So it makes sense that we'll have more base than we will have acid if we're a basic solution, okay? So the concentration of hydronium is less than the concentration of hydroxide, which makes sense because if we have a basic solution, we want more of the base there, okay? And that means that the concentration of hydronium is less than 1.0 times 10 to the negative 7, and the concentration of hydroxide will be greater than 1.0 times 10 to the negative 7, okay? So hopefully the word format or the picture format, something along the way made sense to you, because we're going to do some problems right here. All right, so let's calculate the concentration of hydroxide at 25 degrees Celsius when the concentration of hydronium is equal to 1.5 times 10 to the negative 9 molar. And let's determine if the solution is acidic, basic, or neutral. Okay, so what we want to do is we want to go ahead and write out the fact that Kw is equal to the concentration of hydronium times the concentration of hydroxide, and also that Kw is equal to 1.0 times 10 to the what, you guys? Negative 14. And we're solving for concentration of hydroxide. So with the magic of algebra, what we're going to do is we're going to say that the concentration of hydroxide is equal to Kw divided by the concentration of hydronium. And if we just plug and chug, what that's going to give us is 1.0 times 10 to the negative 14, because that's a value for Kw. And we're going to divide it by the concentration of hydronium. Now in this solution, the concentration of hydronium is not 1.0 times 10 to the negative 7. It gives it to you right here. It says it's something different than that. Okay, so somebody has adjusted those amounts, so it's different. So we want 1.5 times 10 to the negative 9. Now this is a point where you guys are going to have to get to know your calculators and know how to do the exponent functions for your calculator, and you're going to see that you're going to get 6.7 times 10 to the negative 6, and that will be molar, and that'll be OH minus. So what on earth does that mean? How do we know if it's acidic, basic, or neutral? Well, all right, we've got a concentration of hydroxide of this. So let's go back to our chart and look at where a concentration of hydroxide is about 10 to the negative 6. Okay. So let me erase some of this down here. Or just erase all of it. There we go. Okay, so right here would be 10 to the negative 6. And so we had 6.7 times 10 to the negative 6. And we're looking at a concentration of hydroxide. So that's why I chose this bottom part of the picture and not the top, because we're talking about concentration of hydroxide. And we remember that we said right in here where we have 1.0 times 10 to the negative 7, that is neutral. Well, at negative 6, we are right to the right of that neutral zone. So we are in a spot where we have a higher concentration of hydroxide of OH minus than H plus. And you guys can see we're in the basic zone over here. So we'd go back to this problem and we'd say this is a basic solution. And if we think about this, when we're neutral, we're going to have 10 to the negative 7 here. Well, 10 to the negative 6, that's actually a bigger number than 10 to the negative 7. So there's more hydroxide or more base ions in this solution than there would be if it was a neutral solution. So if there's more hydroxides, if there's more base than there would be in a neutral solution, it should make sense that the solution is basic. Okay? All right, number 2 says calculate the concentration of hydronium at 25 degrees Celsius in a solution that has a concentration of hydroxide of 1.3 times 10 to the negative 10 molar, and determine if the solution is acidic, basic, or neutral. Okay, so again, we've got Kw is equal to the concentration of hydronium times the concentration of hydroxide, and we know that Kw is 1.0 times 10 to the negative 14. Now this time we're solving for hydronium instead of hydroxide. So we go ahead and we do the magic of algebra, and we have that hydronium is equal to the concentration, is equal to Kw divided by the concentration of hydroxide. And now we just plug and chug. So Kw is 1.0 times 10 to the what? Negative 14. And the concentration of hydroxide in this solution is what? It's given to you up here. It's not 1.0 times 10 to the negative 7, okay? It has been adjusted. So it's 1.3 times 10 to the negative 10. And what that is going to give us is 7.7 times 10 to the negative 5 molar H3O plus. Okay, so hold on, I'm going to sneeze. Excuse me. Okay, so in this problem, we're looking at a concentration of hydronium, which is different from the previous problem where we were looking at a concentration of hydroxide. So we have a concentration of hydronium, which is acid, that's 10 to the negative 5. And remember, if you have a concentration of hydronium that's about at 10 to the negative 7, that means your solution is going to be what? Neutral. Now 10 to the negative 5, is that bigger or is that smaller than 10 to the negative 7? It's actually bigger because it's less negative. So you have a solution where you have a concentration of acid that's higher than you would if it was neutral. So probably we're thinking this is what kind of solution if you have more acid sitting around than you would if it was neutral. It's probably acidic. And if you have no idea what I just said, let's go back to the chart so we can see it in a visual. Okay, so this time we're taking a look at concentration of H plus or H3O plus here. And we're looking at a concentration that is something times 10 to the negative 5 here. So we can see here that 10 to the negative 5 is more acidic than 10 to the negative 7. So we are right here in the acidic zone. So this is an acidic solution. Okay, now number 3 says calculate the concentration of hydronium at 25 degrees Celsius in a solution that has a hydroxide concentration of 1.0 times 10 to the negative 7 molar, and determine if this solution is acidic, basic, or neutral. So this one is easier than it looks. We should recognize this right here, in that Kw is equal to the concentration of hydronium times the concentration of hydroxide, and this is equal to 1.0 times 10 to the negative 14. So if one of those components is 1.0 times 10 to the negative 7, then the other one is going to be what, you guys? Is going to be 1.0 times 10 to the negative 7. And we saw that back here. In neutral solutions, they both have a concentration of 1.0 times 10 to the negative 7. And that's going to end up being 1.0 times 10 to the negative 14 when we multiply them together. So both of them are 1.0 times 10 to the negative 7. So if we want to officially just write the answer, okay, and you can also put that on the end if you feel like you need to be super specific. And this one is neutral because the concentration of our hydronium and the concentration of our hydroxide are the same. They're both 1.0 times 10 to the negative 7. And back here on the chart, it shows you that. 1.0 times 10 to the negative 7. 1.0 times 10 to the negative 7. That is where we are neutral. Okay, so this seems like a whole lot of math and a whole lot of oh my goodness to find out if something is, if a solution is acidic, basic, or neutral. And the question is there an easier way? And the answer to that is yes, there is a simpler way. And that is using pH and pOH, and we will talk about that in the next lecture. Okay, bye-bye.